There's somebody who is going to talk about his world records. But don't worry, we are not going to be short of world records in this session. So who believes that infrastructure is a commodity? That you cannot distinguish, you cannot differentiate, that everybody uses the same, and all the value creation only comes from what you put on top of it? So who believes that? I mean, raise your hands if you believe infrastructure is a commodity. It's good because then I know the people I need to focus on during the next 30 minutes or so in order to tell you what's still being very actively researched on, because I'm a researcher. I have the honor to lead a 100 people world-class scientist research team in Zurich, Switzerland, not far from here. Infrastructure is heavily being worked on. There is game-changing technology coming up. This is what I would like to share with you, because when you see what's coming at the horizon, you can better prepare. You can take the steps in order to make your infrastructure as cloud service providers become the best for certain workloads, for certain client needs, and distinguish yourselves. But let's now look into the future. And I'm going to take you through essentially 3 basic things. It's a little journey that I'm going to start from the bottom here, how we store data and how we will store data in the future, more and more, how we move data, and finally how we compute on data, and how we may even at some point, for certain types of workloads, not even need to move data when we compute on it. That sounds a little bit strange, right? But this is also the purpose of my presentation, to tell you game-changing, fundamental technologies that we are working on that will reshape the world of IT in the coming years. You may have attended a presentation by one of my colleagues from research yesterday, Jeremy Shaw, working on quantum computers. Who has attended the quantum computing talk? Quite many of you. Was it really mind-boggling, and could you follow everything he said? Probably not, right? This is, let's say, at our doorstep. The things I'm going to tell you about are sometimes at our doorstep or even like really real. I mean, these are not things that we can imagine doing in the next 5 to 10 years. Quantum will become real very soon, right? And we have many customers looking at it very seriously today in the banking business, for instance, because there are changes there that will make you lose or win in the future if you know how to handle this quantum technology well or not. But there are other things here I want to talk to you about, starting with storing data and how this is going to change fundamentally. We are pushing the limits, and this is the name of the game, pushing the limit in terms of density of storage in order to reduce costs, because we have so much more data that we need to keep for big data, for AI, for compliance, for governance reasons, and you know that. I'm going to focus on 2 technologies, because that's the ones that we tend to less talk about, and tell you what we are actively doing in that space. As a member of the scientific community working on enhancing our capabilities to store data. Does anyone here guess what I'm showing on this page? Yes? A tape drive. But it's not your standard tape drive. It's one that is sitting in the basement of my building. It's the one that we experiment with in order to prove data points I'm going to show you next, right? It's not the one that you will go and hopefully buy in a nicely form that's about that size, that can go and enter, standard racks and so on. We are far from that. This will become your standard tape drive in 10 years from now, or beyond, right? The technology that we use here gives us the guarantee, as much as you can say that in 10 years from now, we will be able to productize the technology that sits in the lab here and demonstrate a data point, and this is what is very important, a data point that is represented by a little blue star here, which says 201 gigabit per square inch, spurted tape. That's a detail, we don't need to go over that now. This little star tells you something that is excessively important, and this is why major cloud service providers in the world, and I'm not going to name them now, but they are the most well-known ones, the ones that store lots of data, why they are all jumping and buying thousands, if not tens of thousands of tape drives with multi-petabytes or up to exabytes. This is what I'm hearing from Chinese CSPs now, willing to go and get exabytes of capacities to store data. This little blue star essentially is their guarantee, because it means that over the time we have been able to relentlessly and consistently show tape demos that increase and increase how much data we can store per certain surface on the tape media. And we know that over time, it takes about 10 years before we can commercialize this technology. So we have done the basic fundamental research in order to guarantee that in 2028, right, 10 years from now, we will ship this. And having this curve here is essentially your life insurance. Tells you that you can keep the costs of storing more and more data in check. And the fact that it keeps growing nicely, it shows here a nice line, but keep in mind this is a logarithmic scale, so things are going like this, really. This is really good. And what's particularly interesting also is when you compare this to other curves for different mass storage magnetic technologies, you see that their curves are sort of reaching plateaus, right? I mean, there are still ways to improve, but not at the same rates as we have seen in the past, which means the gap between these tells us that for certain type of data that you don't need immediate access to, this technology will be the best TCO, is the best TCO, and will remain so in the future. Unless somebody comes with a breakthrough technology, which can always happen. I mean, research, right? I mean, this is what you have to account for. At the moment, we don't see any other ones on the radar. The other thing we looked at is beyond just the tape technology, density increase, and so on, is like, how do you make that technology consumable in a cloud setting? And what's the language that cloud applications talk when they access storage? Well, these are object APIs, be it S3, be it Swift, and so on and so forth. The downside was when these object APIs were introduced, they were not meant to interact with media of high latency. They were meant to do a GET or a PUT request and get an instant feedback that here is your data, or yes, we have stored your data on some mass storage devices. Therefore, the community and IBM, together with the rest of the community, decided to change that situation and extend these object APIs with very basic primitives that give the applications the visibility to where the data sits, whether it can be immediately accessed, whether it can be first, it has to be first recalled from tape, and it will take seconds, minutes, until it can then be used by the applications. When you put the applications in charge, when you put the developers in charge, and they have the visibility to what's going on, we can be much more intelligent. We don't have to go and assume, oh, because the data didn't come back right away, there is a problem, there's an error. We have to start a costly error recovery procedure, and that will essentially not bring anything more, right? Because the data cannot come faster than it comes when you have a robot that has to pick a tape on the shelf and bring it into a drive, and then we have to spin the drive and so on and so forth. It takes sometimes seconds, tens of seconds, or minutes. But this is the best TCO technology out there today. So you need to consider that, and with these efforts taking place in the open source community, where we are making this available for free, open source, right, with other parties, I think this should ease the entry barrier to adoption of this technology. As I said earlier, major cloud service providers have large data footprints for which they are already taking advantage of these technologies. I'm not going to spend too much time on this, but to tell you that when you have tape technology with high latency, you can combine it with AI in order to predict accesses to that data even before the users perform their first GET operations to that data. So by bringing the two together, we have the ideal mix. We give you the best TCO technology out there to store data, and with AI, the users never see any latency, or 99.99% of the time, they don't experience any latency, because we predictively prefetch data from tapes, bring it to disks or flash, until the users go and access this. And there are ways we can do this. I'm not going to spend more time on it, but we see significant improvements when we bring these AI technologies into the mix. So that was one end of the spectrum, tape, best TCO, essentially the media for your long-term data conservation, governance, compliance reasons. At the other end of the spectrum, there is flash. So everybody talks flash. What are the challenges today with flash? Of course, is the race towards increasing density and lowering the costs. And how do we do that? Well, essentially, we do this in multiple ways. But what I want to focus on now is where the industry stands, which is 3D TLC, which means stacked layers of flash, each of the cells in the flash systems storing 3 bits. This is what it means, 3D triple level cell, 3D TLC, where the industry is going beyond that with quadruple level cell. And what are the challenges this brings in order to take advantage of such flash technology in an enterprise-grade environment? Because it's fine to use in my phone and whatever other consumer devices. But when you talk about using this in an enterprise grade where you have heavy workload, constant write streams and so on, you kind of stress this technology in a way that may hurt. Therefore, you need to come up with smart schemes. Some of them are described here. This is what we have been like now for many years in my teams responsible to help the development product teams to ship in these nice boxes you see here. But when I explain this, people say, okay, so, well, okay, there are some cool things behind that. What if I explain to you in more detail one example? Then you understand the difficulty, the research challenges, and essentially why we're spending so many resources, so many researchers in the world to tackle that problem. I chose to tell you only one thing about flash. One example of this secret sauce. So something looks, yeah, it's fine here, actually. How do we squeeze more write cycles from flash? I mean, this is the name of the game. When you write to flash, you destroy, physically you destroy the media, little by little. It's like you print with your inkjet printer, each time you empty your ink cartridge a little bit more and more. And at some point, even though the ink cartridge may still be 20% full, the printer says, okay, change the ink, and you're like, what? Come on, not possible, I only use 80%, why can't I use the full amount that is in this damn ink cartridge? And, well, this is the same thing here. How can we guarantee that as we use flash, we use it to the maximum? And there are many ways to do that. First, you avoid writing to it. I mean, if you can write less to the flash, of course you're going to extend the lifetime. How do you do this? Data deduplication, compression, copy data management, all these techniques that avoid essentially writing the same things many times. But when you end up writing to your flash, there are ways you can write it in a smarter way in order to make sure that each of the blocks, these are just a number of cells that are packaged together on the media, that each of these blocks age relatively consistently. And there's a good reason why this is important. Think about your Tetris game, right? You play Tetris, we all play Tetris, right? And at some point, essentially, the screen becomes so full of pieces that you didn't get a chance to like appropriately rotate and drop, that you don't have space anymore and you lose, right? Because there's still space on your screen, right? But there's space that you cannot access, right? This is the same thing. In Flash, you end up often with underutilized flash blocks that still have a lifetime. They are not dead yet. We haven't destroyed the transistors in them, but you just cannot use them anymore because of the same Tetris problem. So this is what you see. The spread here shows you all the life, let's say, aging, relative aging. When you are towards the top here, you are very, let's say, close to retirement flash block. When you are at the bottom here, you are still relatively healthy. This is indicated by what we call the raw bit error rate. The bit error rate, I mean, when you write to it, does it really stick, the data that you write to this block? And this is as you go and write more and more times into your flash device. A normal flash device will essentially have a really high spread, lots of empty spaces in your Tetris picture. What we needed to do was essentially to go and refine this, to ensure that everything ages according to raw bit error rate uniformly. And when you do this, you extend lifetime, let's say by a factor 2. That's one element of the secret sauce. The ones that I presented I showed you briefly on the previous page also help us increase by a factor 2 or 3, each of those. When you bring them in combination, you may get 10 to 20 times longer lifetime, which means you don't change your SSDs as often, and it's the same game as the ink cartridges. You save money because, I mean, you make that last longer. Okay. We talked about storage, tape, and flash, and I hope you get a sort of a feeling now of the challenges that are behind that and why we need PhDs and the like in order to address them. Second problem I would like to tackle here is moving data. So we move data a lot in a data center, in a network, and so on. There are studies out there by Facebook and others that say, well, the links that we use to move data, they often stay on, although there is nothing to be sent. And sometimes this is actually very low utilization of these links. Now, you need to power these links. It consumes a lot of energy, especially when you go to the high multi-50 or more gigabit per second rates. We are talking about 400 gigabit per second Ethernet coming at some point, right? This is consuming a lot of energy. And this is energy you cannot use for other things. If you are using energy in your data center to move things, you cannot use to power the cores, to compute on things. And this is a big problem. So let me explain and give you two numbers. One is a multiply operation on a CPU can take about 1 picojoule. I mean, you know what a joule is, right? A picojoule. It's tiny, but you do a lot of multiplication operation, hopefully, right? In order to move the operands for this multiply operation, we take 320 picojoule. We spend a lot of energy to move things around versus what we actually use to compute on things. And this is what we have to start to worry about. As we want to expand and increase the density of our data center, this becomes a key issue. I mean, just a few examples here. These are the characteristics in terms of bandwidth, memory, number of processors, and measure of single-thread performance of some of our big iron technology, mainframes, Z systems, and so on. And you see that maintaining high system bandwidth to increasing amount of memory is really what the clients are looking for. We have to push the boundaries in there, but for this we need game-changing technology. So here is what I just described. You have your bandwidth demand on a link. I mean, we say that typically at certain stage in your networking hierarchy, you are really using 10% of the links of the time, right? So it's very low utilization. So this is your utilization. You have something to say, nothing to say, something to say, nothing to say. The blue line shows how much power is consumed. All the time, the link is powered. If we could switch on and off the link fast enough, this is all the wasted power we could save and use for a better purpose, like powering your cores, or maybe even increasing the total bandwidth that you are feeding into your cores, because you have more energy that you can ship faster your data into the cores. And this is what we have done. My team have essentially shown a way to do 5 to 6 nanoseconds, so rapid on-off, that we can turn on completely the entire circuitry. So these are CMOS circuits with optical links, receivers, and so on. I mean, moving things and having them on and latched and synced on the clock of the link in 6 nanoseconds is, believe me, I mean, is a challenge, right? It's not something that every CMOS circuit designer can do just like in the morning. It took us a while to show that we can do this. We can, therefore, switch off to very low power very quickly and bring it back on very quickly as well. So in the end, if you look at if you had kept your link on all the time, which is 128 milliwatts here, and you have different packet sizes, I mean, this is a detail, you see that the actual power that you consume, if you use rapid on-off, can be 85% less. Because we can bring this game-changing technology, rapidly switching on and off the networking links, we can save substantial energy and use it for better purpose. All right, so we talked about links at the hardware level. Now there is another piece of I/O that I would like to touch on, where there is still substantial improvements to be made. So my team back in the research lab did the following experiment. They measured how much time it takes to run in a cluster certain benchmarking workloads, and you see the names here, probably you're familiar with some of them. And we changed just one thing from each run to the next. We changed the networking technology used underneath that very same cluster from 1 to 10 to 40 gigabit per second. Then we rerun the experiment and we measure the time it takes to complete the benchmark. You see substantial improvement from 1 to 10. Well, you could expect that. From 10 to 40 gigabit per second, you see marginal improvement. And then you wonder, why did I spend all that money, whereas my applications essentially don't see any benefit? And I mean, we are engineers in the room. We know that essentially the smallest bottleneck in your stack will essentially decide your overall performance. And what has happened here, the bottleneck has moved. The bottleneck is not in the networking layers anymore. It's higher in the OS I/O stacks, and that's what's becoming the limiting factor, because we cannot run these I/O stacks on the processors fast enough anymore. And these I/O stacks have grown over the years. Nobody wants to touch them anymore, right? There are tens, hundreds of thousands of lines of code that sometimes you don't even know what they are still doing, but nobody wants to go and change. So what do? We need to have a disruptive way to take advantage of these fastest and fastest technologies at the networking, but also at the storage layer. And we cannot really go and rewrite an entire I/O stack that has been developed over decades. The approach is essentially to say, well, this is the I/O stack, right? These are all the things that you have to go through when your application, be it a Spark Analytics application, will want to do broadcasts and shuffles and what's not types of operations using the underlying hardware, networking, and storage technology. Well, you spend a lot of money on the hardware, you have higher throughput, lower latency, your applications may see 2 times better performance. This is not sufficient. And we are essentially hindered by this legacy out there. So what we did is, we said, okay, the heck with the legacy. Let's bypass it. And for certain types of workloads, we call this intra-job storage. So while the Spark application runs, it needs fast access, but that doesn't have to be persistent storage. I mean, if the thing disappears because there is a crash or something, you just restart your Spark Analytics job. You just lose a couple of minutes. This is fine, and it should not happen very often. We create a buffer storage layer that is very quickly accessible, that is not protected, that will lose data if power is gone and things like that. But most of the time, we will really be able to leverage the advances at the lowest hardware layers. So we call this Crale. There is no play on words or nothing. It's just a funny name that the teams decided to use. It's open source. It's an Apache incubator project, so it's not just any other open source activity. It's an Apache incubator project. There is a community behind it, not just IBM, right? And just to convince you once more of the potential benefits we can achieve, this is running a Spark workload on an open power cluster that was a 10-cent thing done a year ago in China. You see essentially the time it takes to complete that benchmark. You change nothing in the hardware, nothing, not even the networking. You replace, now you add this kind of cut-through stack so that you don't go through the old I/O legacy code. You use Crale instead for that, and you see 6 times performance acceleration just by bringing different types of software in the entire stack. And you did not change your Spark Analytics at all. The Spark code developers don't see a change, right? This is what is important. So we touch on 2 things in terms of moving data. The hardware layer, how we can really bring game-changing technology by doing rapid on-off with ever faster increasing bandwidth links that cost us more and more power to sustain. And the second thing is how we can address the I/O stack problems, legacy, bottlenecks, using also disrupting technology in the software layer. And now we are touching something which is going to be, I would say, not shipping in the next 18 months. That is not yet an open source project that you can leverage, unlike what I've just shown you earlier. But this is mind-blowing. I mean, you've seen the quantum things. I hope I can really describe the message behind this, because it is different. It is complementary to quantum, right? I mean, we live in a world where things become more hybrid. We take advantage of more exotic technologies, be it GPUs, being FPGAs. There will be quantum that will be used for certain tasks. Not everything, of course, right? And there is something else here, which we call in-memory computing, or computational memory, if you like it, which is also going to revolutionize the way we do IT in general. So first, before I talk about that, let me explain what's the business as usual way of improving IT. Well, first, you can do this. You can take advantage of new, what we call storage class memories, and there are such new type of SSDs with technology that will replace or extend from what we know with flash today, that is on the market already. You can bring computing closer to the memory, so you offload some tasks that are done in the CPU so that they can interact very closely with the memory and don't require to move data back and forth all the time. It's called near-memory computing, also quite becoming more and more popular. Or you can also take drastic steps into packaging things much closer together, right? If the data, the network, the storage, all of this is being like compressed into the same chips, then you can expect also some acceleration because you need to spend less energy to move things around. That's business as usual. That is going to happen. This is happening already now. But there's something that goes beyond that. This is what I call computational memory here. Again, a complement to the existing architecture. It's not going to replace everything. Same that quantum is not going to replace everything. It's going to be a substantial accelerators, and I'm going to give you two examples where we see phenomenal differences when we take such an approach versus the classical approaches that we are all familiar with. So only certain tasks will take place in memory. This is not a general purpose computer. This computational memory can do certain things depending on the characteristics of the devices we use in there. So what are these devices? Are there any electrical engineers in the room? I mean, raise your hand, electrical engineers, the ones who have studied Ohm and Kirchhoff's law at school, at university. Okay, there are some. For the others, I mean, you know Ohm. I mean, this is how you measure the resistance. You know maybe Kirchhoff. I mean, these are also very important fundamental theories that I will not go through right now because we don't have the time. And this may sound a little bit exotic. Here you have actually the layout of this new computational memory. Cells that are interconnected in some way. Each of these cells is not DRAM, it's not a traditional transistor. Instead, it's a new type of memory, which is called phase change memory, that is also used in 3D XP technologies today, but we use different characteristics of this memory. The fact that it can act as a memristor. Who has heard the word memristor? Not too many. Okay, a memristor is essentially a resistance which can change its value depending on how you act on it. Normally, a resistance has a certain number of ohms, 50 ohms, and it's always that much. A memristor is something that will change this value in a dynamic fashion. Therefore, you can store something in there, change it from 10 to 50 to 100 ohms. It's like acting like a memory. And this device here, this little piece of phase change memory material that only takes about 10 nanometer in size, so it's like a neuron, I mean a neuron is about the same size, is what we are using in order to take advantage of these capabilities. What it can do, and this is really the breakthrough. When you do matrix vector multiplication, right, can be relatively complex, takes time to do on a normal GPU. You can do it in place, meaning that you put the coefficients in there. First, you have to go and program the thing. And then you let the memory come out with a result by itself. You don't need to do anything. You don't need to move any data. You just read out the results. This is just plain Ohm and Kirchhoff's law exploitation at its best. It takes zero complexity, O1 complexity versus much bigger complexity if you had to go and program this on a standard computer. But now let me show you what we can do with this, right? This is the foundation behind it, but what can you do with it really? So one example, you can do image compression, decompression, reconstruction. Remember, these devices I showed you are analog devices, right? They're not 1, 0. They have varying levels of conductance or resistance. So they're very analog devices. So the calculations that we do with them are not like precise as they are when you do it with a standard CPU. There will be variations. The material may not react all the time the same way, right? But this is okay because when I show you these two images here, one is essentially the original image, the other one has been reconstructed using many of these matrix vector multiplications that I showed on the previous page, using this computational memory, of course. You barely see any difference. There is a bit of noise, but for this application, who cares? You don't see the difference, or you barely see it. It's good enough for that. And when we use this technology instead, we see 50 times power reduction compared to using a 4-bit FPGA optimized matrix vector multiplier, right? 50 times. How many times do you hear in your career that, hey, I can do things 2 times better, 4 times better, but like orders of magnitudes better? And there's still more to come here on the next page. The other example I wanted to show you is temporal correlation detection. You have, let's say, many streams of events, discrete events, coming in. And your goal is to detect among all these streams which are the ones that are correlated, right? Simple correlation detection. You can program that on a standard computer. And we will show you in a moment how efficient this can be done. With computational memories, we can take advantage of their dynamic properties in order to, by itself, detect which are the streams that are correlated together. So, give you an example, this could be tweets. Discrete events, tweets coming from different channels, different people, and you want to see, you have 1 million tweets coming, you want to quickly see the ones that are coming from similar sources, because they may be correlated, they may be coming at the same moment in time. Just one simple example. There are many more you can imagine also. So, here is the example I wanted to show you that we have designed and experimented with in our labs. We take 1 million streams, so it's an image of 1,000 by 1,000 pixels, if you like, right? And the pixels are being activated at some point in time. This is discrete events, right? And you see when they're activated, the little dot comes here. You barely recognize anything here. However, across this million pixels, some of them are correlated. There is some information that is hiding behind that. This is sort of the insights you want to get from all your big data, but you just cannot see it. You could compute, use brute force, and we'll show you in a moment the cost of doing this, or you could use computational memory to go and do the same thing. And if you click on this black square, now you will see slowly, and this is really the time it takes in order to capture this correlation among the pixels. You should see slowly a picture coming up. Shows you how correlated all these streams are, and this is showing you a map of the world, right? If you had done this with standard computers, and this is my last page, you would have gone, could have taken you a lot of time, and as you increase the number of streams, it takes you always more time, right? You can imagine this. And we did that. We used the best IBM Minskys, the newest Power 8 generation. Well, it's not the newest anymore, but it's a Power 8-based generation with NVLink and GPUs and CPUs. We did our best, and this is essentially how this problem scales as you increase the number of streams. If instead we use computational memory, we do it 200 times faster. So how often do you hear somebody comes and tell you 2 orders of magnitude faster, more efficient, versus standard architectures? I bet not very often. All right, so compute in place, first message, move way faster the data and consume less power. Second message, store data much denser using tape and US flash technology. That was my third message. There is a booth you may have seen already out there, and you are welcome to go and visit us. There is actually, standing on the booth, hardware with encryption and I/O devices that include technology coming from my lab, so I'm very proud, and I can talk to you about it in more detail if you like. But, well, I want to thank you for your attention and welcome any questions.